Hello and welcome to the start of Mechanics 1, and in this video we're going to be introducing the idea of momentum and impulse as well, actually. Okay, now I want to actually start off with a little question here, okay, a little thing to think about. So you can see here I've got an image of a feather falling and a football, okay, and I want to ask what is easier to catch out of these two things, okay. So I'm asking this because this basically will demonstrate what momentum is, okay? And hopefully you can imagine that it's going to be far easier to catch the feather than a football that's going to belt at you at full speed, okay? So hopefully with me here that the feather is going to be easier to catch as it falls down, right? But why exactly is it easy to catch? Okay, we know intuitively and like common sense wise, a feather really easy to catch, right? But why is it easier to catch than a football at full speed? I guess there are two main factors. Okay, well, obviously the speed is going to be one of them. A feather that's just gracefully falling down to your hand, it's going to be a lot slower than the football at full speed. So the speed is going to be one factor. So the speed is slower. But actually also, another factor would be the sort of the mass, or kind of like the weight of how heavy the object is. Okay, a feather is really light, isn't it? But a football is a bit heavier, so it might be harder to grip, to get into your hands and stuff like that. And you're going to need a lot more force and energy to be able to capture the ball. Okay, so a feather is really light, which makes it easier to grip and get a hold of. So there we are. So I'm going to say a feather. So as the feather is lighter, okay? So these two are the main factors why, more precisely, the feather is easier to catch, okay, compared to the football here, okay? So hopefully that makes sense. So this is essentially the idea of momentum then, okay? So momentum is basically to do with how easy it is to stop or catch something, okay? So momentum essentially describes how easy it is to catch or stop something, okay? And that's really it. And so if we look at our example then, we saw that these two factors affected how easy it was to catch, or how it affected the momentum more precisely, right? So we looked at the speed and its sort of weight, okay, how light or heavy the objects were, okay, to look at their momentum. So what we can say is that the factors of momentum are, so momentum is affected by speed and its sort of heaviness or lightness, right? So what I'm going to say is it's affected by the velocity, right? Now velocity is sort of the more technical term for speed, okay? It's because velocity is speed, but it tells me what direction, okay? We're going to look more into that if you haven't already in mechanics, but velocity is essentially speed, okay? And then obviously what the idea of how light or heavy is, okay, that's going to be what we call the mass, okay. The mass is essentially the number on the scale which tells me how heavy or light something is, okay, not the weight. It's really unideal how in real life we use weight to determine how heavy or light something is, but technically it's weight. That's called mass, okay. Weight is something different, but mass is sort of tells me how heavy or light something is. And so there we are. So velocity and mass, okay, tells me something's momentum, okay. So hopefully that made sense. That's sort of the main idea of momentum. Tells me how easy or hard it is to catch or stop something from moving, okay? And it's affected by its velocity and its mass, okay? So its speediness and how heavy or light it is, right? Which makes sense, right? Because if something's really fast and it's really heavy, it's going to be very, very hard to kind of stop it from moving, right? Think about a heavy boulder moving down a hill. It'd pretty much be deadly to try and get in front of it and try and stop it, right? So that's the idea, okay? But that's the idea. But what about a sort of mathematical formula then, right? Now, as we've seen, because momentum is affected by velocity and mass, we could say that the formula for momentum is velocity times mass, okay? And there we are. And that's a key formula we will be using, okay? Sometimes this is written as, in letters, P is mv, okay? Where P is momentum, m is mass, and v is velocity, okay? But that's my formula, okay? Now, as for the units, well, velocity is effectively a speed, okay? Again, it's a bit more, it tells me speed in a direction, okay? So if I'm moving forward or backwards, whatever, right? So it's to do with speed, so it's going to have the units in meters per second, okay? But I'm going to write it like this, okay? With a sort of s to the -1, okay? You might be familiar with from G to C, seeing it as a meters per second like this with a sort of a dash, okay? But this is a division, right? Meters per second like this is saying meters divided by seconds. But then if you think about your power laws, that's just ms to the -1, okay? So these units are the same thing, but we're going to use the sort of more grown-up unit, okay? And use ms to the -1, okay? From here on out, okay? Anyway, that's the unit for velocity, meters per second. Mass, again, it's a weight. Well, not a weight, but it's like how heavy or something is. So that's going to be in kilograms, okay? Okay. And so then momentum, the units for momentum, where we can just times the units. So we're going to get kilograms, meters per second like this, okay? And that's my units for momentum, okay? Not the nicest looking units, but that's the units, okay? So that's essentially my formula. Momentum is velocity times mass, P is mv, right? So that's momentum. Okay, and the last thing we need to look at is changes in momentum, okay? So let's have someone on some sort of surface or floor, okay, like that. And they move to 2 points, okay? So initially this person is here, right? Then finally they're at this point, okay, there, right? Now they're going to have different speeds, okay, between or velocities between these 2 points, okay? This person's movement and their speed is changing. So initially they have a speed u, okay, u meters per second. So u is is this person's initial velocity or speed here, right? And then finally, then have a speed v. Okay. So we can work out the change in this person's momentum as they move from these 2 points. Okay. Now the mass of the person is m. Okay. Let's just call it m. Okay, m kilograms, that's the mass. So we can work out the initial and the final momentum. So the initial momentum, well, if the initial velocity is u and the mass is m, well, it's just going to be mu, isn't it? Then we can work out the final momentum, the momentum at the final point. Again, if we apply momentum, which is velocity times mass, well, the final velocity is v and the mass is m, so it's going to be mv at the end of there, okay? So therefore the change in momentum, well, it's going to be the final momentum and take away the initial momentum. or we could then sub in our numbers, and then final momentum is mv, take away mu for my initial momentum. Okay, so the change in momentum is just mv take away mu. And so to help visualize what we mean by change in momentum, I have this little photo here. So we have a snowball that is falling down a snowy hill, right? And so as you can see, the idea is the snowball is getting bigger and bigger, right? As you get more and more snow, right? So the snowball is getting bigger and bigger, okay, as it falls down. But also as it falls down, you're going to get faster and faster as well, right? So the idea is the snowball is picking up more speed, but it's also getting bigger, okay? So its velocity and its mass is getting bigger and bigger, okay? So that means its momentum is going to increase and increase and increase, right, as a result, okay? And so the change in momentum is going to be bigger and bigger, okay? So its momentum gets larger and larger as it gets bigger and bigger, the snowball, right? So that essentially means the snowball becomes harder and harder to slow down and try and stop, okay? And so there we are. So because it's harder to stop as it gets bigger, its change in momentum is bigger. So hopefully that made sense, okay? So that's the whole gist, all right? So if something gets bigger, or if it becomes faster or something like that, then it will result in a bigger change in momentum as its momentum increases, okay? Right, so now we're going to look at some questions. And firstly, I just want to look at some questions where we use the formula, right? So we get comfortable with the idea of calculating and using momentum, okay? Now remember, momentum is velocity times mass, and that's the formula we will be using, okay? So firstly, we need to find the magnitude of the momentum of a cricket ball of mass 400 grams moving at 18 meters per second. Okay, so firstly, my mass is 400 g. And what's my velocity going to be? Well, it's going to be the 18 meters per second, okay? Now, I can't work out momentum just yet because mass is not in the units we want. Mass has to be in kilograms, okay, before we apply the formula. Velocity is meters per second, so velocity is fine, okay, that's in the correct units, but mass isn't. So we're going to need to convert grams into kilograms. Well, how do we do that? Well, we're going to need to divide by 1,000, right? So it's going to be 0.4 kilograms, okay? That's 400 grams is 0.4 kilograms, okay? So now we can work out the momentum using the formula. It's velocity times mass, so it's going to be 18 times 0.4, which will be at 7.2, okay, and the units are going to be kilograms meters per second because we just timed the units, okay. Then for part B, we have a lorry of mass 5 tons, okay, so the mass is 5 tons, and I'm told it's moving at 0.3 meters per second. That's the velocity then, right? 0.3 meters per second. Okay, but again, the issue is that mass is not in kilograms. Here it's in tons. So we're going to need to convert it into kilograms, okay? Now, a ton is 1,000 kilograms, okay? So actually, to convert tons into kilograms, well, we're going to need to times by 1,000. So we get 5,000 kilograms, okay? So 5 tons is 5,000 kg, okay? And so now we've got the correct units, we can work out momentum, okay? So that's going to be, again, velocity times mass. So 0.3 times 5,000. And so that will get me 1,500. Okay, and again the units are kilograms and meters per second. And there we are. Okay, so again, make sure your units are in kilograms and meters per second. Okay, but there we are. And then we've got this question here. So here we're told an object with mass 4 kilograms is initially moving with velocity 20 meters per second. It then speeds up to velocity v meters per second. The change in the object's momentum is 36 kilograms per meters per second. Find the velocity v. Okay, so it's talking about change in momentum here, right? So the change in momentum, right, is mv take away mu, right? So m is my mass, v is my final velocity, which is the v here, and u is the initial velocity, which is 20, right? So the change in momentum we're told is 36, so we could say 36 is equal to mv take away mu. The mass is 4, so it's going to be 4 for m, 4 lots of v take away 4 lots of u, which is the initial velocity 20. Right, hopefully happy with that. So I've just subbed in the numbers into my formula here, right? So I can now simplify this. So 36 is going to be 4v take away 4 times 20 is 80. Okay, then if I solve for v, so 4v, if I add 80 to both sides, I get 116. And then to get v, I can then divide by 4. Okay, so v, divide by 4, I get 29. Okay, and that is my final velocity there, right? Okay, now we're going to be looking at impulse. Okay, so impulse is linked to forces, right? So as an example, let's say I have someone that is pushing some sort of crate forward like that. Okay, let's say there's a force of, let's say, I don't know, 500 newtons. Okay, so this person is consistently applying 500 newtons to push this block forwards, right? But what we're going to look at is we're going to be looking at sort of the total time. Okay, because what we're going to be interested in is, okay, well, you're applying this force, but how long? Like, how long is the force applied for? How long are you pushing the box forward for, right? Because that gives us a sense of sort of the total force applied, right? Because it's the force for how long. Okay, and so that's the idea of impulse, right? So impulse is force times time. Okay, so how long are we applying the force for? Okay, so in this example, okay, well, the force is 500. Okay, and let's say the time is 30 seconds. Okay, so therefore the impulse of the force is going to be force times time. So it's going to be 500 times 30, which should be 1,500. Okay, and the units are in newton seconds. Okay, because we times the units, right? So force is newtons and time is seconds. So we times the units to get newton seconds. Okay, so the units for impulse are newton seconds. Okay, so hopefully happy with that example. So we literally times the force by the time. Okay, so that gets me a sense of the total force. Okay, the total or the full effect of the force. Okay, so how long I've applied the force for. Okay, so that gets me a sense of that, and that's the impulse. Okay, so that's what impulse tells me. Okay, so impulse tells us the sort of the total force applied for the whole duration. Okay, so that's the idea, right? So it's the force and for how long we applied it for. So hopefully that made sense. Right, and because impulse is essentially telling us the total force applied, right? Okay, so the force applied for that entire duration. Okay, if I think back to this example, so I said I'm pushing this crate forward for 30 seconds. Okay, I'm pushing it by the same force for 30 seconds. Okay, so the impulse will tell me, well, it tells me the total force, so the force for the whole 30 seconds. Okay, and so you can kind of think of it then as the total push. Okay, so it's how much I pushed across the whole time. So you can kind of think of impulse as also sort of like a pushing effect. Okay, so impulse is effectively describing a pushing effect to move an object. Okay, to move an object forward. Okay, because that's essentially what it's saying, right? It's the total force applied, effectively, right? So it's got to be the pushing as a result, so how much I pushed an object overall. So hopefully that makes sense. That's the whole idea of impulse. So we can calculate impulse by doing force times time, but actually there's another nice way of working out impulse involving momentum. Okay, and we can also work out impulse to be the change in momentum. Okay, but we know change in momentum is mv take away mu. So what we could say is impulse is alternatively mv take away mu. Okay, and there we are. And this is what we call the impulse momentum principle. Okay, this equation here. Okay, so this equation links momentum with impulse. Okay, and this is called the impulse momentum principle. And so we have two different ways of calculating impulse. So remember, the other way, as we just saw, is impulse is also force times time, or ft for short. Force times time, F times t. So we've got these two different ways of working out impulse, and usually it's going to be really obvious in a question which formula we can use because they're quite distinct. Okay, one will involve force and time, the other one will involve speed. Okay, and so there we are. But I would say in this course, like 99.9% of the time, you are going to be using the first equation here, the impulse momentum principle, to work out impulse that way. Okay. In fact, I haven't seen an exam question so far where we have to use this formula involving force and time. Okay, but you do need to know both these equations. Okay, so we can work out the impulse that way. And so there we are. Right, so again, I want to look at some questions where we just use the formulas. Okay, so we're comfortable with the formulas. So here we're told a body of mass 2 kilograms is initially at rest on a smooth horizontal plane. Horizontal force of magnitude 4.5 newtons acts on the body for 6 seconds. Find the magnitude of the impulse. Okay, so there's a lot of fancy language, right? But it's essentially asking us to find the impulse. Okay, and so how are we going to calculate impulse? So remember, we've got two equations. We've got impulse is change in momentum, so mv take away mu. But we also have impulse, sorry, to be force times time. Which one are we going to use? Well, actually, spot. We're told the force and we're told the time. So we're going to be using this formula to work out impulse. Okay, we can't use the first one because we don't know what the final speed is. Okay, anyway, so impulse is force times time, F times t. Well, force is 4.5 newtons times the time of 6 seconds. So if we times them together, we get an impulse of 27 Newton seconds. And there we are. Hopefully happy with that. And then in part B, then it wants me to work out the final speed. Okay, well, now we can use the first equation, right? because that's going to involve speeds. So impulse, so impulse is mv take away mv take away mu. But we just worked out impulse to be 27. So 27 is going to be mv take away mu. Now the mass is 2, so it's going to be 2 lots of v take away 2 lots of u. Now u is my initial speed. Now I'm told it's initially at rest. Rest means it's not moving, so it has no speed. Okay, so rest means no speed. So it starts off with 0. Okay, so we get 27 to just be 2v. Then we can divide by 2 to get v. So v is 27 over divided by 2, which will be 13.5. Okay, and that is my final speed v there. Okay, and then I've got this question here. So we're told a ball of mass 0.5 kilograms is at rest when it's struck by a bat and receives an impulse of 15. Find the speed immediately after it is struck. So okay, which formula are we going to use? Well, hopefully you can spot we're going to be using this formula. So impulse is mv take away mu. Okay, my change in momentum, because there's no mention of force or time. Okay, it's all to do with speeds. Now we're told the impulse. Okay, the impulse is 15. So, and we're also told the mass is 0.5. So it's 0.5 lots of v, my final speed, right? My final velocity, take away 0.5 lots of u. Now u, again, it's initially at rest, so the initial speed has to go to 0. Okay, hopefully you're happy with that. So 15 is going to just be 0.5 v. And then I can divide by 0.5 to get v. So 15 divided by 0.5 will get me 30, right? And there we are. That is my final speed, okay, afterwards. Then I've got this question here. So we've got a toy car of mass 0.2 kilograms is pushed from rest along a smooth horizontal floor by horizontal force of magnitude 0.4 newtons for 1.5 seconds. Find the speed at the end of the 1.5 seconds. Okay, so what a bit going on here. So okay, so there's a mention of force and time again, right? So I reckon we can work out impulse by doing force times time, right? F times t. The force is 0.4. The time is 1.5 seconds. If we times that, we get 0.6, okay? 0.6 Newton seconds. That's my impulse, okay? So hopefully happy with that. So impulse is the force times time there. But it doesn't want the impulse, it wants the speed at the end. Okay, the final speed. Well, we can use the other formula then, right? So impulse is now mv take away mu. Okay, well, we know what impulse is. It's 0.6. We just worked that out. Then m, my mass is 0.2. Lots of v, which is what I want to work out. Take away 0.2, lots of u. Now u is my initial speed, but again it starts at rest, so it has no speed initially. Okay, so again we get this equation. So 0.6 is 0.2v. Then if I divide by 0.2, I get v to be 0.6 divided by 0.2, which is 3. Okay, 3 meters per second, and that is my final speed there. Okay, so hopefully you're comfortable with the formulas here. Okay, with these two formulas. Okay, so impulse is force times time, and impulse is change in momentum, or mv take away mu there. Okay, now we're going to be looking at some harder problems involving bouncing off walls and the ground. Okay, and this is where we're going to have to start doing some diagrams, right? So the first situation we're going to look at is bouncing off a wall, right? So let's have, for example, we have this ball here, then we have the wall. Okay, so I have my ball and then the wall. Now, if you can imagine, for example, throwing like a tennis ball, at a wall, okay? Hopefully you can visualize what that's going to look like. So before, the ball's going to move towards the wall, okay? And then afterwards, it's then going to rebound off the wall, okay? Move backwards, okay? So hopefully you're happy with this. Now, what exactly is causing this sort of motion where the ball goes towards the wall and then back off it, okay? That's to do with impulse, right? It's to do with the pushing involved, because what's happening is the ball and the wall are going to push into one another. So firstly, the ball is going to push into the wall forwards like that. So the wall will receive an impulse, okay, like that, okay, impulse forwards like that. Likewise, then the wall will also push into the ball backwards. So the ball will receive an impulse backwards, okay, and that causes the ball to push backwards, right? So the wall pushes the ball backwards, so the ball would bounce like that. So that's what causes the motion, okay, and that's the impulse, right? Impulse is the pushing effect. And so there we are. So hopefully happy with that then. Hopefully happy with the impulses involved. We can also look at things bouncing off the ground in a very similar way. So let's say we have the ground, okay. This is my ground, and then again have the ball bouncing off the ground. So this is my ball. So before the ball's going to bounce, it's going to touch the ground like that. And then it's going to bounce off the ground afterwards like that. Okay, so hopefully happy with that. So the ball goes towards the ground and then it's going to bounce off the ground. Okay, now again, what's causing that motion? What's causing the ball to bounce off the ground? Again, imagine like a tennis ball, something like that. Try and just imagine throwing the ball off the ground. Okay, it's going to imagine that motion, right? What's causing that? Again, it's to do with the pushing and the impulses. Okay. So firstly, the ball is going to push into the ground like that. So the ground's going to get an impulse downwards, okay? Then in the same way, the ground will also push into the ball and it will push the ball upwards. So the ball gets an impulse forwards because it's being pushed forwards, right? It's the pushing effect. So the ball will be pushed forward by the ground. And that's what causes the ball to bounce up, because the impulse of the push forwards, upwards, right? And so that's the idea here. So hopefully happy with that diagram as well. So that's the impulses involved. Okay, that's what's causing that's what causes things to bounce off walls and bounce off the ground. It's the impulses and the pushing involved between the ball and the surface. But hopefully happy with that. And so we're going to look at some questions involving this now. So we have this question here first. So we have a ball of mass 0.2 kilograms which hits a fixed vertical wall at right angles with speed 3.5 meters per second. The ball rebounds with speed 2.5 meters per second. Find the magnitude of the impulse exerted on the wall by the ball. Okay, so we're going to need to draw a diagram, but it's talking about a wall. Okay, so it's going to look like this. So I have my ball and then I have my wall here. Okay. So there's my ball. Now the ball has mass 0.2, so I can add that on, 0.2 kilograms. So as you can imagine, the ball's going to go towards the wall, forwards like that. And I'm told the original speed is 3.5. Okay, so the speed before hits the wall is 3.5 there. Then it's going to rebound, okay, bounce off the wall. And I'm told afterwards the speed is 2.5. Okay. So hopefully happy with that so far. So it wants me to find the magnitude of the impulse exerted on the wall by the ball. Right, so what is going on there? So the impulse exerted on the wall by the ball. So the ball is pushing into the wall, as we discussed. So the wall will receive an impulse here. Okay. Now, you might then think, well, I can calculate impulse by saying it's the change in momentum, mv take away mu. Right, I can do that because I got my two speeds and I got my mass. However, the impulse here is on the wall. The wall doesn't have that speed. It's the ball that has the speeds. The wall, I can't do anything to the wall. But what I also know is the the wall will then push into the ball in the same way, and the ball will receive an equal impulse like that. Okay, so what I can do to find the impulse is just work out the impulse here for the ball. Okay, now before I can just sub my numbers into this formula, the other thing to pay attention to is the fact that directions matter. Okay, and this is why it's so crucial to do a diagram here, because you can see the direction things are moving at. What do I mean by that? Okay, what do I mean by that? So I'm going to say directions matter. So as you can see here, the impulse and this speed here is moving to the left. It's moving backwards, right? But this speed is moving forwards. So some things are moving forwards and some things are moving backwards. That actually matters, okay? That does matter, because the things moving backwards is sort of in the negative direction, right? And so I'm going to say that backwards, like this. So the backwards is the negative direction, and forwards is the positive direction. Okay, so what I need to do to account for the direction is, when I now sub my numbers into this formula, I need to negate anything that's in the negative direction. So, for example, the impulse here is in the negative direction, it's going backwards. So I'm going to need to do minus I. Okay, the minus tells me it's going in the negative direction. Okay, so minus I is going to be mv take away mu. Well, the mass is 0.2. Okay, then v, my final speed or my final velocity, is 2.5. But v is not going to be 2.5, it's going to be minus 2.5, because that's also going in the negative direction. So you must negate things that are going in the negative direction. Okay, in this case it's backwards, right? Then I'm going to take away mu, so 0.2 lots of u. Now u is going to be 3.5 and it's going forwards. Okay, so it's going in the positive direction. So it's just going to be plus 3.5 here. Okay, so it's just positive, right? So if I now simplify this, I can now solve for I. So minus I is going to be minus 2.5 times 0.2. That would be minus 0.5. Take away 0.2 times 3.5, and that would be 0.7. So therefore, minus I is going to be minus 1.2. Then I could just flip the negative to get positive I is 1.2 Newton seconds, and that is my impulse there. Okay, so there we are then. So again, it's important to note that the directions matter. Okay, and so you can use this little rule here. So things are going in the backwards direction, it's negative. Forwards direction, positive. And so there we are. Okay, you could actually flip it the other way around if you wanted to. So you could say that forwards is a negative direction, backwards is positive, like that instead. Okay, and then minus I will then become plus I, minus 2.5 will then become plus 2.5, and then plus 3.5 will go to negative 3.5. So because then the directions reverse, right? But usually it makes a lot more sort of sense and a lot more intuitive to basically say that backwards is negative and forwards is positive, right? I think that makes the most sense, but to treat it that way. But you could flip the directions if you wanted to. But there we are. So do pay attention to your directions, okay? And then negate things that are in the negative direction, okay? Then we got this question here. So we're told a ball of mass 0.2 kilograms moving along a horizontal surface hits a fixed vertical wall at right angles. The ball rebounds at right angles to the wall with speed 3.5. Given that the magnitude of the impulse is 2 Newton seconds from the speed of the ball before it hits the wall. Okay, so it's talking about hitting the wall again, right? So it's going to be the same sort of situation. Like this, okay? So this is my ball. The mass is 0.2 kg. Okay, so the ball's going to bounce into the wall forwards like that. Then it's going to rebound backwards like that. Okay. And so then there's also going to be an impulse. So the ball will push into the wall like that. Okay. And then the wall will also then push into the ball backwards. So the ball will have an impulse acting backwards like that because the wall is pushing into the ball. Anyway, so there we are. That's my diagram. Now the speeds. I'm told the speed after it rebounds is 3.5. So 3.5 is my speed afterwards. Okay. I'm also told the impulse. Okay, the impulse is 2 Newton seconds. So 2 here. So 2 Newton seconds. So I need to find the speed before. Okay, I'm going to call that U. Okay, U for my initial speed. Hopefully happy with the diagram then, right? So hopefully happy with that. So now, if I was to apply my impulse formula, so impulse is mv take away mu. Well, in this case, again, the impulse is acting in a negative direction, right? It's going backwards. So it's going to be -2, not +2, -2, because the negative accounts for the negative direction it's going in. Okay, hopefully that made sense. Then mv take away mu. Well, mass is 0.2, lots of v. That's also going in the negative direction, so it's -3.5 to account for that. Take away 0.2 lots of u. I'm just going to call that u, right? And that's going in the positive direction. It's going forwards, so I don't need to negate the u there. Okay, so it's just positive u. Anyway, hopefully happy with that. Now we can just simplify this to solve. So -2 is going to be -0.7 minus 0.2u. Therefore, at 0.2u, okay, is going to be 1.3. Therefore, if we divide by 0.2, so 1.3 divided by 0.2, I get 6.5. Okay, and that is my initial speed u there. Okay, now we're going to be looking at things dropping on the ground, and I will say this will require some knowledge from normal maths mechanics, okay, from year 1. It's possible you could be starting this chapter, this video, at like the start of year 12, where you might not have seen any prior mechanics, okay, but we are going to need some prior knowledge. So essentially what we can do is use what we call Suvat equations, which are these 5 equations here, to work out missing quantities, right? So we can find the time in a journey, or the distance or displacement technically in a journey, or the final and initial velocity or speeds between a journey, or its acceleration. Anyway, hopefully you are familiar, but there could be a chance you might not be, if you, depending on how early you're looking at this chapter. Okay, but anyway, let me just set the scene, right? So we've got a ball of mass 0.2 kg dropped from a height of 2.5 meters above horizontal ground. After hitting the ground, it bounces to a height of 1.8 meters above the ground. Find the magnitude of the impulse received by the ball from the ground. Okay, so it's talking about things dropping off the ground. So again, we're going to need to draw a diagram, right? So obviously we've got the ground here. Now what we're told is the ball is dropped from a height of 2.5 meters. So the ball starts up here, right? Then it hits the ground here. So this height is 2.5 meters. Okay. So initially it's going to start with 0 speed. Okay, so 0 meters per second, that's my initial speed, because you can imagine if I'm dropping it from a height, I'm sort of letting it go from my hand. I'm releasing it from my hand, right? Imagine I'm holding the ball with my hand and then I'm letting go. It starts with 0 speed, right? Then when it reaches the ground, it's then going to have a speed v at the end, okay? Now, what you also need to know, which again you should know, or you will be seeing if you haven't already, from mechanics and normal maths, is that the acceleration here, okay, which I'm going to draw like this, deceleration when things are falling down, okay, is what we call G, okay. But G is a number. G is 9.8 usually. So I'm just going to say 9.8, okay? That's my acceleration. Meters per second squared, written like that, okay? So I'm going to lay it out then. So S is sort of my, it's going to be my distance, my height here, which is 2.5. U, my initial velocity is 0. V, my final velocity is V. I'm just going to call that V. And then A, my acceleration is 9.8. Okay. So there we are. So now what we can do is, now that we've listed what we've got, we can look at my survey equations. Okay. So I want to find the equation that does not involve T. Okay. T for time, because that's not what I've got here. I've only got S, U, V and A. And actually, if you stare at it, okay, the equation that ignores T is this fourth one here. V squared is U squared plus 2AS, okay? So V squared is U squared plus 2AS. And so I can sub my numbers in, okay? So V squared is going to be 0, add 2 lots of 9.8, 2.5, okay? So that was simplified to V squared to be 49, okay, and quite nicely, if you root that, then you're going to get root 49, which is 7, okay. So V is 7 here, and there we are. Then what we're told is after it bounces off the ground, it bounces up to a height of 1.8 meters. So let's say over here then, the ball now moves up. And then it moves up to here. So the height it bounces up to afterwards is 1.8 meters. Hopefully you can see that here. Hopefully you're happy with that. And so in this case then, if I call U here to be my initial velocity or speed after it bounces off the ground, and then it reaches up to a final speed, okay. Now actually at the end of this, okay, if I look at the end, okay, when it reaches up to the maximum height, it actually ends up to 0 speed, okay, because it can't move anymore, okay, because then it's going to drop back down again, okay. So it ends up with 0 speed. So hopefully happy with that. Okay, so if I kind of separate the motion, right? When it bounces off the ground, it has initial speed U, and then it ends up with 0 speed, and it travels 1.8 meters. So hopefully happy with that part. Okay. Now the acceleration is still acting downwards by 9.8. Okay, that will always be the same. Okay, so if I now focus on the second half when it bounces off the ground, so S is going to be at 1.8. U is going to be, well, U, okay. V is going to go to 0. Okay, that's the final velocity. Now, acceleration is still going to be acting downwards by 9.8, okay. So I'll do it here. So 9.8 meters per second squared. So the acceleration's acting downwards, but hang on, everything else is acting upwards, right? The object is moving up, the ball's moving up, but the acceleration is acting downwards. So directions matter, right? So what we need to do is negate the acceleration to be minus 9.8, okay? To account for it going in the opposite direction, okay? Because what we're effectively saying here is here upwards is positive and downwards is negative, okay? So the directions matter. So things are going downwards here, okay? In this part, then it needs to be negated. Now, just to clarify, with the first part, right, everything was moving downwards, so it didn't really matter which direction to take, positive or negative, because everything acted in one way because it was moving downwards, right? So we took downwards to be positive instead, okay? Because the ball is moving down, we can take downwards to be the positive direction for the first half, but then with the second half, because the ball's now moving upwards is positive instead, okay? So hopefully they made sense with the directions. Anyway, so we have this situation, right? So again, we can apply the formula v squared is u squared plus 2as. So in this case, I want to work out u. So v is 0. So 0 squared is u squared plus 2 lots of minus 9.8 for a, and then 1.8 for s. So I'm going to get u squared minus 35.28 is 0. Okay. So that just gets me u squared to be 35.28. Then I can square root it, right? So just u then becomes 5.94, okay, to 2 decimal places. So that is my initial velocity there, 5.94. Okay, so 5.9. Okay, and there we are. Right, but it's actually asking for the impulse. Okay, so what I'm now going to do is consider the impulse, right? I'm going to draw the situation as the ball hits the ground, okay? So the speed that the ball goes into the ground is 7, right? So it has 7 speed before it hits the ground. What about the speed after it hits the ground? It's 5.94, right? So hopefully happy with that. So these are my speeds before and after it hits the ground. But I want the impulse. Now, the ground is going to push into the ball like that. It's going to push the ball forwards, upwards, right? So the impulse will act up like this. Okay, so to find the impulse then, impulse is mv take away mu. Therefore, impulse is going to be the mass. The mass is 0.2. Lots of v. Now v is my final. Is my final speed or velocity, which is 5.94. Okay. Take away 0.2, lots of u. Now u is 7, but that's acting in the negative direction. It's going downwards, right? So it's going to be minus 7. Okay. So if we simplify this, we get impulse to be 2.59, okay, Newton seconds, and that's to 2 decimal places. So that's my impulse, okay, and there we are. Okay, so we're going to finish up with an exam question. So here we're told a small ball of mass 0.3 kg released from rest from a point 3.6 meters above horizontal ground. The ball falls freely under gravity, hits the ground, then rebounds upwards. In the first impact with the ground, the ball receives an impulse of 4.2 Newton seconds. The ball modelled as a particle. Find the speed of the ball after it hits the ground. Okay, so we have to draw a diagram then. So it's hitting the ground, so it's going to look like this. So the ball is being dropped towards the ground like that. Okay, so initially it's at rest. It's released from rest. So it starts with 0 speed. Okay. And then as it hits the ground, that's going to be the final speed here, v. Okay. And then I'm told it drops 3.6 meters. So this whole distance, this height is 3.6 meters. Okay, so hopefully happy with that. Okay, now also the acceleration is downwards by 9.8. Okay, that's always going to be the case when it's dropping down like this. Okay, so we can firstly use my Suvat equations to work out what v is, because if I list it out, S, my distance or displacement here, is 3.6. U, my initial velocity is 0. V is V, right, and then A, my acceleration is 9.8. Okay, so actually, again, I'm gonna be using the this equation here, right? V squared is U squared plus 2AS, because it's the only one without T for time. I don't have any time here. So V squared is U squared plus 2AS. Then I can work out V that way. Okay. So V squared, if I sub the numbers in, I'm going to get 0 squared for U, and then 2 lots of 9.8, lots of 3.6. So that gets me V squared, if I work that out. I get 70.56, and then if I root that, I get V to be, if I square root, 8.4. And there we are. V is 8.4 meters per second. And so there we are. So 8.4 there. Right, but then it's asked me to find the speed of the ball after it hits the ground. So then it's going to bounce up off the ground like that. Okay. But actually, I'm told the impulse is 4.2 newtons seconds. So if I consider the impulse by doing this diagram here, then, right? So again, the ball at the speed of the ball before it hits the ground, as we just worked out, is 8.4. Okay. And then let's call this speed afterwards. I'll call that a different letter W, right? Okay, not to confuse you with the V we just worked out before, okay? It's a different speed W here. Anyway, so 8.4 is my speed before, then W is my speed after it hits the ground. Now, the impulse again, the ground is going to push into the ball, push it upwards. So the impulse of the ball is upwards. And also, I'm told that the impulse is indeed 4.2. So I can sub that in. So 4.2 here. Newton seconds. So now my impulse, again, I is mv, take away mu. So in this case, the impulse is 4.2. So 4.2 for I. Then m, my mass is 0.3. Okay. So 0.3 for m. Then v, my speed afterwards, I'm going to call that w, right? So w here. Take away m, which is 0.3, lots of my initial velocity. Now that is 8.4, but that's going downward in the negative direction, right? Everything else is acting upwards, so downwards is negative, so it's going to be minus 8.4, okay, to account for the negative direction downwards. Okay, then if we simplify this, we get 4.2 to be 0.3 W plus 2.52. Then we can solve the W, right? And then we've done it. So 0.3 W, if I rearrange, 4.2 take away 2.52 gets me 1.68. Then divide by 0.3. I get W to be 5.6. Okay. And that is the speed after it hits the ground there. Okay. And so there we are. So hopefully that has helped. But that's it for now. But I'll see you next time.